Yeah, so thanks for having us. So Martin and me, we're colleagues. We're 2 of 8 of Recogni. Obviously a wordplay with recognize, so we're about recognizing things in visual data. And I was Logan's eyes with intelligence. That actually means something. It's not just sounding nice, and I'll get into that a little later. So what is the problem with this guy? What is the problem with AI? It's kind of that everybody's using his stuff. So everybody uses NVIDIA right now, right? And it's pretty amazing what they've enabled over the last couple of years. It's also pretty amazing how their stock value increased. And they pretty much have a monopolistic, or they had a monopolistic position in 3 markets, so computer graphics, AI, inference and training, both of them, and crypto mining. So when we talk about training and inference, it's actually 2 disciplines that have very different needs. And we're an inference company, we're not a training company. We also do train our networks, obviously, but we're building a solution for inference at the edge. And you have a couple of dimensions in which requirements change. So for example, mathematical operators, when you do backpropagation, you have to divide stuff. You don't do that in normal CNNs if you do the forward pass. Next one would be the resolution requirement. Because of vanishing and exploding gradients in deep neural networks, you have to use pretty high precision floating point numbers even. And again, in inference, you can optimize for something completely different that goes all the way down to maybe 3 bits or 1 bit even. Latency is another thing, right? If you upload your picture to the Google Cloud and you want it to tell you what's on this picture, like a holiday picture, and it tells you, gives an automatic tag. Maybe Instagram is also doing that. I don't know, I'm not on Instagram, but automatic hashtags. Basically, you don't care if this happens in 3 seconds, in 10 seconds. So latency is not really an issue here. However, if you have a system that's running at 60 frames per second, everything has to happen in 60 milliseconds again and again and again. The real-time capability in terms of throughput. So again, if Google realizes, okay, having more and more users using our speech recognition, for example, we're going to scale up our servers, right? A drone that is living off a battery cannot just do that. It has to work with whatever is there in hardware. And of course, the power consumption. So what we're definitely aiming for is also the last point, cooling. A lot of applications have to be passively cooled. So you can't have an interface to the outside world by using a fan, for example, or even liquid cooling is too complex. And of course the size. Our chip is very small. The V100 chip that you see here by NVIDIA is the biggest that you could currently manufacture. And I think the development costs something like 3 billion. So the inference efficiency of NVIDIA, even the newest architecture, the newest benchmarks on a ResNet 50 normal classifiers, 0.16 TOPS per watt. Intel Mobileye with the newest product launch in 2020 is already much better. Grok is at an even better stage. But all that still means that if I want to understand, really understand a human crowd with 100 people, something that a human can do in real time, you easily get to a power consumption of 1 kilowatt. What do I mean by that? You look at the latest and greatest algorithms from Facebook to classify actions of humans, for example. If you multiply that with how it scales up for high resolution so that you can actually see pretty far, and you can actually see, if you have a scope of 100 people, for example, on an intersection, or what a car could see driving through an inner city, and then you multiply, for every human you have to know the body joint coordinates, you have to know, you have to classify the action, what they're doing. It can go as far, like, I've recently been at the ECCV with Martin and we've seen some great research, for example, people understanding how fast you're breathing, basically super fine optical flow on pixel levels that actually tells you in a huge crowd you can identify someone who's suddenly breathing quickly. But why is that, right? That could mean that, for example, they need help. There's some kind of an emergency going on, or it could mean that suddenly their heart rate goes up because they're just about to maybe hit someone, kill someone. So in the case of surveillance, really important. But all of these things are unlocked, not because there's no AI researcher, no smart dude developing that stuff. They are developing that, and it's insane, it's fascinating at what level AI has gotten to, but most of the applications cannot really be deployed, especially not in real-time edge cases. And so someone has to close that gap, and that's why we were founded a couple months, 1 year ago. And we want to enable the research that is happening today. We don't want researchers to wait and wait and wait, like it's been going on for the last couple of years, for NVIDIA, to release the next GPU and the next GPU. And it's ridiculous. Like, some papers claim they're real-time capable and they achieve 25 frames per second. They don't even say anymore on which device, because everybody assumes it's probably a Pascal graphics card. So, the sense of, not a lot of people are sensibilized for that topic. That's also something we good to see. And so, with a couple of, rethinking the whole stack of vision AI at the edge, we came to a number that is arguably higher and can enable a couple of other applications. And I'm not going to get into details how we exactly achieve that, but I'm going to show you a couple of principles that led us towards there. Yeah, what is Recogni? Just quickly. So we were founded mid-2017, couple cool companies. Currently 8 people, 2 in Munich, 6 in Cupertino. So chip design and all that is happening there, and AI is in Munich. So far seed funded and 75% on our way to finishing our Series A raise so that we can actually build the first full system. We're definitely a systems approach. Sure, there's a heavy focus on silicon, but we really try to rethink the whole thing. And I'm going to give an example on the next slide that shows how we were inspired by what nature is actually doing. So this is kind of our product suite. Our visual perception unit, our actual silicon, is embedded into a hardware device that we want to sell for a certain price. And around all that, there's a certain development suite that should enable users to build on top of a lot of things that we develop for them. So that also training times go down, and there's a lot of, the big concept here a lot of times is transfer learning, so that we basically provide users with a strong backbone. And our first market is definitely autonomous driving. So we've divided into 4 categories, basically SLAM, knowing what's going on around you with a lot of depth and point clouds and so on. Classifying what you see, anticipation. So, okay, I understand that right now it's snowing. A car in front of me is wiggling a little bit, so maybe I should, step on the brake because I'm understanding that in the scene right now this car could break out. And generative models, GANs, basically for scene normalization, for example. A lot of neural networks. For them it's easier to recognize stuff, for example, if you take out the weather out of the scene, right, which is possible by now. So yeah, that's pretty much what we want to do, and as I've mentioned, level 4 and level 5 autonomous drive. It's roughly a $15 billion billion market for us by 2025. And the holy grail that we want to be part of enabling is to really fuse very early on in the processing pipeline basically image data and depth data, so LiDAR and image together, which is pretty much aligned with what bigger companies from that space have also told us what they're working on. So the current problem in autonomous drive is the following. If you look at prototypes you see right now, for example Waymo or Aurora and other companies, they're using partially 16 V100 GPUs, so they have a power budget to run these things of a couple of kilowatts. If you really do the math with the next thing that NVIDIA will release, you're getting to a number that is 26 kilowatts. So it's ridiculously high. So that means that if you just have your, if you have a Tesla Model S P100D and it stands on the parking lot for 4 hours just trying to figure out is something going on, after 4 hours the battery will be empty. And we're trying to solve that by having a distributed approach. So all of these recognized symbols are basically visual sensing units, and we are basically doing AI processing right where the image is being created, right where the data is created, and we're stepping away from this ridiculous concept of doing everything in a centralized way, which it really doesn't have to be. So it's roughly a 500x improvement in power consumption. So first learning is neural networks can live at the edge, and by that I mean they can live at the edge. I mean, of course they already can. There already is silicon for that, but they can even do that in these extreme, human level applications like understanding a huge crowd. And the way we got inspired for this is, our brain and our eyes sit close to each other. We have two eyes, so we understand depth. The path from the sensor, our eyes, to our brain, basically our silicon in that case, is very short. So all of these basically learnings is also that when we transfer data from our eyes to our brain, of course there's some kind of compression for sure going on, but it's perceptively lossless. So this whole concept of perception loss, like whatever my eyes see and is important, I will get that. So this is what we got inspired by, and we said, okay, we have to put the silicon very close to the image sensors. And what's interesting here is that our competition is consuming 80%, 90% of their power just for memory transfer. Only 10% is really for doing the computations, for really executing these neural networks. And that's how you build intelligent systems as far as we're concerned. The next thing is you can run neural networks much slimmer. And by that I mean, if you have a neural network and it works fine in floating point 32-bit, that doesn't necessarily, let's say you have a layer in your network and you see, okay, this is my weight distribution right now. So here's 0, and all the way here is some higher number, like maybe 8 or something. This is 6 times standard deviation plotted of a certain variable in a classic CNN. In the beginning it can look like that. So it's just normal distribution, pretty smooth. Now let's have an example. Let's say you want to develop something more efficient. And your idea is to represent a parameter of a neural network in a chip using some weird analog transistor. And it has 3 states, negative, minus 2.3 volt, neutral, minus 0.7, and active 15.3. These are completely invented numbers, but let's say it's like that. So you now have to tell your neural network, please only use parameter values that are this. So how do you do that, right? Because neural networks are creatures that grow organically, right? Like as they learn, they develop their distributions. It's not all there at once. So basically the newest method here is to incentivize your values to be close to the values that you actually want to use. So what you can see here, I'm not going to get into details why we have that scale, but the white traces here are the numbers that our system can use. All other numbers are not possible. And as we train, as we go from 10,000 steps to 36,000 steps to 60,000 steps, you can see that our network has gradually learned, without affecting accuracy at all, that all values should live pretty close to that. And then once you're done with that and it looks even sharper, you can set all values to exactly these values and you've quantized your network. So this is a very soft approach, and it's getting more and more popular, I would say. You can also teach your neural network to only use -1 and 1, so basically 1-bit networks. And what does that mean? I mean, that means that out of 32-bit that people have been using quite a lot, maybe you can actually use way less, right? That's quite an intense message here. And applying this method over and over again, not just on single values, but even on groups of values, we already get to a boosting factor of 10 to 100x compared to our competition. So, when you have some neural network or some machine learning algorithm in general, and you think, okay, what about this weird math? For some reason, I can execute this in a cheaper way. Maybe I only have a small device and it's not going to be able to do divisions. Get rid of your divisions. Somehow find a different way. Maybe replace them by bit shifts in your graph and just let your neural network figure it out if it can still handle it. If you want to use only weird sets of numbers, build your regularizer and losses accordingly and let it figure it out, because that's what backpropagation is for. So far, backpropagation is heavily underutilized as far as I'm concerned, because these tests show that you can get so much more out of your neural network if you just give it a couple more jobs to do. And a free bonus here is even better generalization, yeah? Because if you tell your neural network you're only allowed to use a couple of different values, it'll have to live under that constraint, and living under constraint always means you become a better generalizer. Another really cool thing I saw at the ECCV was, imagine you have, this is pretty much taken from one of the winners of a video segmentation challenge. And I saw this recently a couple of weeks ago at TUM at an ECCV workshop. So the goal here is you have a neural network, you get a couple of frames, maybe, I don't know, a 1 or a 10-second clip. And the goal is to segment different things out of an image, okay, something that is used widely. Now let's say your current accuracy after learning is 75%. Now, what if I told you, you'll now do the following. I'm going to teach my neural network, because I don't want to use a lot of resources. I'm going to teach my neural network to also predict optical flow. Optical flow means from one picture to the next, where did the pixel move? Now, the intuition behind that would be, like, if I would ask you, like, how will the accuracy change? You would probably say, okay, now the neural network, the same neural network with the same size, has now to do two things. So probably the accuracy will drop. But what happened with these guys is that actually it increased quite a lot, actually. So what does that mean? It means that imagine you have a football player and you let him play football for 10 years. And suddenly you get the idea, what if I also told my football player to do some leg presses in the gym? You know, it might be something that he'll never use in the actual game. Like, nobody's doing fucking leg presses on the football field, right? But it tells his body and his brain and his muscle coordination to, you know, learn new things. And I think this approach of, you know, implicit learning is super powerful. And more people are using this, and it really shows that neural networks are heavily underutilized, right? Because, like, in that case, you know, the gradient wasn't moving anymore at the end. Everybody thought, okay, this is what this network can do. But no, it was actually able to also do that at pretty good accuracy. And suddenly, the accuracy in that part, so sorry, maybe that's confusing because that accuracy is here, but actually the accuracy of the main job increased. Because now the neural network has figured out to look for features, temporal features in that case, that can help it with the main task. And now, during training, this is used, but during inference, they just don't care about that output. So, are we really getting the most out of NNs? You know, I don't think so. Get creative. There's a million ways to do it. Yeah. Another thing is neural networks that even have been trained today on low-resolution data, on existing data sets, they can achieve so much more. What you see here is a busy intersection with hundreds of entities that an autonomously driving car might be interested in understanding what they're all doing. What we used here is a pretty good algorithm, object detector for car stuff, or trained on the Kitty dataset, so it's called SqueezeDat Plus. It's a pretty good algorithm, but what you can see is it's not able to detect that car, that car, that car. So after a certain range, it stops, right? So automotive people selling radars are happy about that, because now they can sell their radars, because that car that maybe is 250 meters away, sell a radar for it, sell a LiDAR for it. Image data doesn't reach that far, right? But why is that? Because we're only processing maybe an input frame that is 500 times 250. Because current edge devices are not capable of dealing with more. Now, if you apply the same algorithm to the entire 8 megapixel high resolution frame, you actually get to that. So it's the same algorithm, right? It's pre-trained. We didn't even train that. And this is pre-merging all different zoom levels that we process. But you can see that now suddenly this car detected. Even most entities have been detected a couple of times. Like if you see multiple bounding boxes per object here, that means it's been detected on multiple zoom levels. So what I would say here is that the broad perception, you know, that the neural network, like for people who are a little bit into the field, you know that you can have something on your smartphone and maybe you're filming the table, and then it'll sometimes understand that this is a laptop and this is a bottle. But like the bottle over there, it will definitely not understand. This is not because the neural networks haven't necessarily been trained in the correct way. It's just because we're not processing high resolution data yet. Yeah. So, AI is crouching and we'll try to make it walk upright. So no more unnecessary data paths. Put the eyes close to the brain. So we're actually processing roughly 2 gigabytes of data of 4 8 megapixel image sensors, uncompressed 60 frames per second. And a chip that is directly connected to the image sensor can handle that. It's not really a big problem. Like, maybe it does mean that you're that you're transporting a couple of gigabytes or maybe even terabytes internally per second, but for a 7 nanometer silicon, state-of-the-art silicon, that's not really a big problem. But it is a problem for an Ethernet cable. So no more external memory, not even DRAM, no central computer, no cloud, no uploaded math. We're not using any multiplications, only additions. We're not using floating point, we're using less than 8-bit. We're not using any wide data paths, and all of this is not really needed. No more low quality front ends. We have 4K TVs and cameras, and they're able to record stuff at maybe even 100 frames per second for slow motion stuff. So why the hell are most silicon companies still, issuing benchmarks for neural networks that have an input size of 224 by 224? That's ridiculous. I mean, sure, then they can claim that we're processing 50,000 images per second, but small images. And no underutilized resources. So we're teaching really neural networks to do, or neural network backbones, to be pretty mighty and to not just do one thing, but to do a couple of things, like the guys with the optical flow and video segmentation. And we found that neural networks are good at doing a couple of different things in parallel. Yeah? You don't necessarily have to make them much wider. Yeah, so that's it. Thanks. So, yeah.
What is your your explanation difference from the multitask learning approach that is also quite familiar? Is it something different or is it the same? Because in one example was kind of the same, and in the other one with the resolution it's not the same.
Sorry, with the resolution?
Yeah, it's not multitask learning. I don't know.
Right.
Is there any relationship between these two approaches, or?
Not necessarily. So the resolution thing that we showed, where we detected more stuff, that doesn't really have to do anything with multitask learning. Like it's something separate. It's more that we found, so most neural networks when they process stuff, they keep spatial isolation more or less. So you're actually able to, it's not super hard. Or what we exploit is that you can actually glue together results from different zoom levels. So as you go deeper, more and more zoom levels are fed into the network by kind of skip connections or entry connections.
Go deeper.
More
capacity.
Well, we also go deeper for more capacity. But the thing is that even if you simply train the same neural network to do another task, very often you'll be surprised by that, well, it will actually be able to do it. And the thing is that if a network might seem that it's already maxed out and it's not able to learn anymore on that task, well, that might be true, but it doesn't mean that it can actually learn something new. And the amazing thing with these optical flow people was that the main task even got better. So, I mean, of course, that's not super unknown, right? Like we know that, for example, if we want to be able to detect oranges and apples, it might actually be worth to train first on a data set that detects 1,000 classes, because that's more data and you'll be sensitive to more features and all that. But even completely seemingly different tasks can be handled by the same backbone. So that's I think what more and more people are seeing, and
What is your timeline? What are you going to sell in the end, and when? Roughly?
So what we'll sell is, according to our current plans, go-to-market strategy, is a hardware module that is the chip, a couple of electronics around it, the PCB, and the visual front end. And that now the housing for that, it will not be possible that we also do that. We will cooperate with tier 1 or OEMs in the automotive industry, but it'll also have an external connection for a true depth sensor like LiDAR or radar, so that we can infuse that early on. So that's the current plan for roughly $200 initially per module, and the price for that will go down as the market penetration for these level 4 and 5 will get bigger. When? So we're planning to have it like mid-early 2020.
curious. So you're obviously in the automotive autonomous driving space. What was the initial feedback that you got from all the car manufacturers? Because I could guess that they're kind of working on similar stuff themselves.
Yeah.
And how do you deal with these guys?
Yeah. So it depends a little bit on who you talk to in the automotive industry. I think there's a couple of different categories of people who we could and we have spoken to and we could cooperate potentially. It's for example Uber and Lyft. It's Continental and Bosch suppliers, tier 1 suppliers. It's companies that maybe are doing, for example, AI software stacks. It's maybe companies that are just doing one specific device like Velodyne or Blickfeld, LiDAR or whatever. And it's of course the OEMs like BMW, Conti. I mean, most people say, like, knowing the competitor landscape of AI silicon, what they always tell us is, wow, this is amazing. Like, if this is really true, what you can do, this would help us a lot. The feedback is great, of course, because we're basically, our selling point is pretty simple. It's pretty one-dimensional. We just say that we nail compute efficiency, while staying at a pretty high maximum performance as well. So for them, it's the idea of finally getting rid of actively cooled graphics cards in their cars. Like for example, Artisense, another Munich company, one of them have told me, they don't believe that the eventual solution will be some supercomputer in a car where you can fry your eggs on. Like he said that. Currently it's even way more than that, right? It's a couple of kilowatts that we're using. It's like 4 tea cookers or something that you have in a car to make that work. So the initial feedback was pretty great. The questions then revolved around, if you're doing so many optimizations, so much weird math and all that, can we really execute every neural network on that? And then we get into explanations of why yes and what maybe not. Like we're not good at RNNs, for example, but nobody in vision wants to really use them anymore anyway, I think. At least for most tasks not. And even if you then ask researchers, could you have replaced that RNN block by a CNN, moving window approach, most of the time they would say, yeah, probably. Would have been maybe a little more complex to train it, but yeah. So yeah, the feedback is good. It's mostly the question that Patrick also said, like, when are you going to be on the market? Because that's interesting for us. As long as you don't have a chip, we're not interested in really, like, except for if they might think about investing. But other than that, of course, they want to see something they can play around with.
Maybe as an add-on question, since you mentioned it, you probably also provide interfaces for all the standard libraries, right? Like TensorFlow.
Yeah, so right now we're heavily focused on TensorFlow, so we haven't gone into anything else yet. So let's see how that will be. Yeah.
How have you done tests and benchmarks so far? Like, what kind of hardware have you used? Have you done tests?
Google Cloud. So all our chip stuff is emulated in custom C-level, CUDA level TensorFlow ops that we wrote ourselves. So to have like our custom TensorFlow layers trainable, we've basically all the weird math that we use, we've put it into a layer. And we did that in normal TensorFlow operators, but then it was way too slow, so we had to do it in CUDA and C. And now it's pretty much quick enough, yeah.
So you don't have any chips?
No, we don't do anything on FPGAs, because even a huge FPGA for $5,000 or something, it wouldn't allow us to get to a proof of concept that is in any way impressive, because we have so many weird little optimizations. Like, for example, our memory should be able to efficiently handle 3-bit accesses. Sure, an FPGA can do that, yeah, better than maybe another like GPU, for example, but yeah, it's not really helping us. Isn't it always like that? Could always be like that. We've started quite early on to rethink a lot of AI inference stuff, I would say. So it's also a little bit of a first mover advantage, I'd say. Because most of the other inference silicon that we see is still pretty general purpose. They are using 8-bit, for example, but they're still using pretty normal math. They're still using multipliers. Just getting rid of multipliers gave us such a big boost. And the biggest part is they're all using external memory. So it's not like the image from the image sensor gets directly to the AI chip. It first goes through maybe some other processor, then into some external memory like DRAM, and then into the chip. And during that path, 90% of the energy is already spent. So we get rid of that. All right. Great. Thanks. Cool.